As individuals, how do we create functionality? As individuals, we think and act procedurally. Let's look at this task of mowing the lawn. Suppose today is Saturday and it's our day to mow the lawn. How do we think about doing that? We think about it in steps. First, change into work clothes. Then, fill the canteen with water. It's a warm summer day. Then, get out the lawnmower and check the gas level. Then, start the lawnmower. Then we mow the lawn. Next, we collect the cuttings and dispose of them. And finally, we stow the mower back into the garage. We have thought and acted procedurally to complete this task. When we want to accomplish something ourselves, we think procedurally, step by step. How are we going to accomplish it? As human beings, this is our natural way of thinking. As programmers, creating applications with a procedural language feels natural to us. It conforms to our natural way of thinking. Procedural programs execute a thread of control. As programmers, we create this thread such that our applications will provide the functionality desired of them. As we saw in the mowing of the lawn example, it is natural for us to think of the sequence of instructions which will create the functionality required of our application. However, there is another way to create functionality, a way we are all familiar with. This second way of creating functionality is called division of labor. Division of labor is as old as human society. It was not invented, it simply evolved as the best means of handling societal complexity. Modern societies could not exist without it. Here we see an example of division of labor. Someone wants to purchase a car, so they go to an auto dealership and they interact with an auto salesman, decide on which car they want and the price they will pay. Then they go to a bank and speak to a loan officer who arranges a loan for the car. Meanwhile, the salesperson has applied for a title through the local Department of Motor Vehicles. And when we pay for the car, he gives us the title to the car. The purchase of the car has been made possible through the interaction between 4 different people or entities. Each one of these entities had a specialized knowledge for completing their role in making the purchase of a car possible. Now let's see what purchasing a car would look like when modeled using objects. In this small scenario, we can identify 4 objects: customer, salesperson, loan officer, and the Department of Motor Vehicles. The behavior or functionality knowledge of each of these objects is also shown along with the requests or messages that they respond to. Just as their real-world counterparts, these objects exhibit encapsulation. Although the salesperson has access to the Department of Motor Vehicle object to obtain automobile titles, they do not have access to the department's knowledge base of their state or any other data the DMV may contain which does not immediately pertain to a request for the title of the purchased automobile. The same is true of the other objects shown. For example, the customer does not have access to the salesperson's commission or to the loan officer's salary. Now I ask the viewer to use their imagination. Imagine that you have just returned from a vacation. Your house is for sale, and your realtor calls and tells you that a potential buyer will be stopping by to see the house in 1 hour. There are a few things that need attention to make the house presentable for showing. The lawn needs mowing, the swimming pool area needs cleanup, and the house windows need to be washed. You realize that you cannot do all of these tasks in 1 hour, So you ask your son to clean the pool and your daughter to wash the windows. You will mow the lawn. You are parallel processing the chores to get your house ready for showing. You also don't care how the chores you have assigned to others get done. Your son may ask his younger brother to help or even pay him $5 to do the job while he gets some video game time. You have requested functionality of your son and daughter which they know how to accomplish. Now you can focus on mowing the lawn, knowing that the other tasks will also be completed. What I have just described highlights an important visualization of objects. That is, behavior, or functional, independence. The services an object offers to other objects through its interface only describes the what of the service offered. The how of that offered service is hidden from the requesting object and may even change from one request to the next. Here is another example of creating functionality through division of labor. Here we see 4 objects interacting to complete an order for auto parts. We see the 4 objects one at a time carrying out their responsibilities or their functionality assigned to them. It looks like there may be a thread of control here. Here I am showing the same auto parts order application, but in this version of the application, the business process for fulfilling a customer order has been implemented as a separate object. If there is a thread of control here, it is not very obvious. And what about this object-oriented application, composed of the objects shown in yellow? There are many objects interacting here. There are 2 processes within the application. One is the order process we saw previously, and another is a process for valuing corporate assets. It would be more difficult to visualize a thread of control here. At this point, I would like to make something clear. There may be some of you who are saying that no matter how I am showing these objects interacting, the message passing is taking place sequentially, so that the code within these objects, or the code within this application, is being executed one statement at a time, and the CPU is executing instructions sequentially one at a time. So one could correctly say there is a thread of control in an object-oriented application. But is this how we should be thinking about object-oriented applications? The answer to that question is no. What we should be thinking about is how objects interact, how they are each supplying some part of the functionality of one of these 2 processes within this application. It is also worth noting that the parts object is supplying some part of the functionality in each of the processes, and that functionality may be different for each of those processes. And you probably have noticed that I have not included a separate process object for each of the 2 processes. The reason for that, the diagram would have been too cluttered if I had done that. Earlier, we spoke about division of labor. Now I want to show another kind of division, a division that takes place conceptually within an object-oriented application. Here we have the application we saw in the previous slide. The objects of the application shown with the yellow circles. The application is shown within the large blue circle. Now I would like to ask the viewer to use their imagination for a moment. Imagine that you are inside this application that is running on a computer, and you are at a place inside the application, but a place that is outside of all the objects of the application. Your point of view is at some place in the blue area, let's say at point A. What could you see from this point of view? Well, you could see all of the objects of the application. You could see the message passing between the objects and the responses to each message. You could see the interface of each object, that is, the functions that they are exposing to other objects of the application. But that's all you could see. Due to the encapsulation layer of objects, you could not see anything inside of those objects. You could not see the data, nor could you see the code that is supplying the functionality of each object. Now let's change your point of view. Imagine that you are inside one of these objects, say at point B. From this point of view, what could you see? First, you would probably note that things look very procedural. You would see data and functions that are written procedurally. You can see the interface that the object is exposing to other objects of the application. You can see messages being received and responses being made by this object. But due to encapsulation, you could not see anything outside of that object. You could not see any other object of the application. You could not see the message passing that's occurring between objects of the application. What is the significance of these two different points of view? Inside of an object, you are in a procedural world. Objects are procedural entities. External to the objects of the application, you are in a world where there is no procedural code. In fact, in the world of the application external to all objects, there is no code at all. All of the code of an object-oriented application lies within the objects of the application. There is no code in the OO world of an object-oriented application. That world external to all of the objects of the application, the world of interaction through messaging, the world that I have labeled the OO world. That world is the world of the programming abstraction we call the object-oriented paradigm. The idea of providing the entire functionality of an application using objects is a new way to think about programming. It is a paradigm shift in one's thinking. It is the shift from procedural thinking to object-oriented thinking. When programming procedurally, we think about a thread of control and sequential execution. If we are thinking in an object-oriented way, we think about the interaction of objects within the application. And so, perhaps, the biggest hurdle to making the transition from procedural programming to object-oriented programming is giving up thread of control thinking. Of course, we don't really give up thread of control thinking. In fact, we use it to create the functionality of each object. But what must be given up is thinking of the functionality of the application as being created in some sequential procedural way. For example, seeing the message passing as a sequence of one message after another, and that sequence creating the functionality of the application. The functionality of an object-oriented application is found in the interaction between objects, and messaging is the signature action of an object-oriented program. Simulation is another metaphor for visualizing objects in an object-oriented application. Here are two quotes, the first from Alan Kay, the creator of Smalltalk, the second from Timothy Budd, a professor at Oregon State University. First, thus in object-oriented programming, we have the view that computation is simulation. And then, in brief, in a simulation, the user creates computer models of the various elements of the simulation, describes how they will interact with one another, and sets them moving. This is almost identical to the average object-oriented program, in which the programmer describes what the various entities in the universe of the program are and how they will interact with one another, and finally sets them in motion. What is simulation on a computer? There are many things we can think of here, but the first one that comes to my mind is video games. Think of some video game in which you are fighting an enemy, perhaps an opposing army, or perhaps aliens from outer space. You are picking your target based on your calculations of what will defeat the enemy. The game does not know how your thinking will go, which one of the enemy will be the next to receive your fire, or your laser, or however you are dealing with the enemy. There is no thread of control as you play the game. The only thread is the thread in your mind, the thread of your thinking of how to defeat the enemy, and yet each one of the entities of the game reacts appropriately when your gaming actions impinge upon it. Most computer games are programmed using multi-threading, with a separate thread for each entity of the game. Each entity in a game simulation is, in a real sense, independent. Its only thread of control lies within itself, and it reacts to outside forces in its own independent way. The idea of simulation is helpful to begin thinking in an object-oriented way.